Okay, so I'll be talking a little bit about the HAFLANG project's efforts towards making another special purpose processor for, this time, lazy functional languages, taking a slightly different approach to the one we heard from Carl this morning. I've done similar presentations to this one before, but now we're a little bit more complete because we actually have at least early results for a concurrent garbage collector. And since we're talking about evaluating lazy functional languages, we'll start with some motivation from a Simon. And this is actually exactly the Herculean effort Christian was just talking about, where there is this huge semantic gap between the execution model of your high-level lazy functional language and your actual execution model of your stock CPU, right? And that's just a big gap you have to overcome somehow. So we're not actually proposing that we make optimizations for these architectures. We're just making an architecture to more directly evaluate these programs. And the way we do that is through graph reduction. So if we have a little bit of an intro here. Bastards. Okay, well, this is just an add function, 3 arguments, adds them up with binary primitives. So we're going to look at some abstract machine state here, only doing the application of this function, not going any further and actually reducing to a normal form, just the function application. So we can imagine we've got 3 memories, a stack, a heap, and some code memory. In our code memory, we have just a graph representation of the function body, right? So we've got an inner and an outer. On our stack, we have our function and its arguments. So you can imagine all we really want to do is take a copy of our graph structure there, resolve some arguments, and actually allocate those, or distribute them somehow between the stack and heap memories, and that's it. So we get something a bit like this. We've popped some stuff off the stack, added some new things, and instantiated some heap application. That is the transition we kind of want when we do function application. And it looks like a simple thing because it is. Maybe we could do that in a single cycle. That would be the goal. So let's see what happens if we take that same example and just push it through GHC. And this is without any optimizations enabled. So it's not representative of what you would actually run in this case with the primitive addition, but it is the general case that you need for graph reduction. So imagine the assembly adding 3 numbers. Yeah, okay. And this doesn't even do the addition. This is generating that graph structure that then reduces to the answer. So what's the challenge here is, well, each of our applications, we're building up kind of piece by piece, because we've got one quite narrow interface out to, well, logically one single memory. So all of those applications we were pushing about instantaneously on paper, they're now kind of sequentialized. And we've also got some runtime stuff, checking for stack and heap space. And if we run out, we have to throw our hands up and go to the runtime system. So we really want to do something much more like the first diagram, much closer to what we do on pen and paper. The 3 opportunities. Does anyone know if we can get rid of this bar somehow? Can you? With the green bit? Oh, great. Thank you. Okay. The worst thing is in the recording, you can't see that, so I'm going to look like a complete nut job. The 3 real opportunities we see when we're thinking about making custom architectures for graph reduction is, one, there's some sorts of parallelism that kind of exist within a single function. So there's not really much in terms of data dependencies between the different things we were moving about in our example. So if we can come up with some nicer memory structure, maybe we can exploit that a little bit better. And that's particularly a concern, this memory bottleneck for lazy functional languages. Because sure, we've got immutability, so we're allocating lots of things all of the time, but we're also allocating funcs. So that's kind of a a big pain point for a sort of conventional evaluation of these things. The second point, as with any kind of managed language, we're going to have runtime system tasks, garbage collection being the big one. And they're hard to do concurrently to the useful work in software implementations. So again, as we heard this morning, maybe with custom hardware, we can make that work a little bit better. The third one, well, long promised, yeah, you've got pure languages. Surely we can exploit lots of parallelism just automatically and implicitly. And I mean, to a certain extent, maybe that's true. In fact, some places in the room that can tell me that should be true to some extent. That would be really, really cool to exploit a sort of parallel multi-core architecture, right? So this talk is about the first two, and I'll get some hints on the third one at the pub. So let's look at our machine then that we've actually got to do this graph reduction. And I'm afraid I'm going to kind of blast through some of the details. I do have a previous presentation, which is that QR code, that lingers a bit more, and it comes more from a language side. This is going to be more from a hardware architecture side. And hopefully an IFL paper published quite soon. There was a conditional acceptance for that we got, but that will have all of the kind of real nitty-gritty in it. So if we just think of like the simplest way we could evaluate that first example that we had, we get something that looks actually identical to Leonard Augustin's big word machine, which was this architecture he proposed in, I think, 91. Really just with a single observation that, yes, this memory bottleneck is a real issue, but we can widen that by having, well, big words. So your heap is working over entire applications rather than over kind of atoms within those. The complementary thing to that is you then need a stack structure where you can permute like the top n elements. And the way you achieve that is through a big kind of crossbar interconnect. But really that is the gist of the big word machine. There's only ever two sorts of instructions. One that builds some kind of big arbitrary complex application and allocates it on the heap, and one that does the same and then permutes the stack instead of the heap. If we're working with integers, sure, we'll need some ALU. Probably the more interesting element is this update stack. So with graph reduction, once we take something off the heap, we evaluate it, we would usually, in the general case, then need to write that back to the heap, overwriting the previous value. So if that expression was shared, we don't reduce it twice. The way we do the bookkeeping for that is really just the easiest way is to keep a stack of, well, something saying when we should do those updates and where we should update. So that is the kind of foundation here. One really neat trick that is also in this paper is saying, well, actually doing these updates is still quite costly. So whenever we can avoid doing it, we should. And you can avoid doing it when you know the thing you've evaluated is definitely not shared. So there's no risk in it being evaluated more than once. The way he was suggesting you do that is kind of unique to these custom architectures because it's doing runtime dynamic analysis that would be really quite expensive to do in software. And this is actually an idea from a previous project, the SCIM project in the 80s. But really, it's a one-bit reference count. So you tag every single pointer with the flag saying, is this pointing to something shared, possibly shared, or is it pointing to something that's definitely unique? And the circuit to implement the tagging there is absolutely tiny because you just say, well, if I've duplicated it, set those bits. That's it. But we're talking about garbage collection later on. So remember, that is called one-bit reference counting rather than anything to do with update avoidance. Turns out they're the same thing. So if we advance that a little bit further, we get the reducer-on architecture, or at least as it was last published. So they were taking very similar ideas and trying to push towards this goal of being able to do an entire beta reduction in a single clock cycle. And depending on how big your functions were, they achieved that. So the steps towards getting an architecture that will do an entire super combinator beta reduction in one cycle, well, yeah, okay, make a Harvard architecture. We've got separate heap and code memories. Now it's very common to have dual port memories, so let's not only be able to allocate a single wide application on the heap, but let's do two simultaneously. These templates, by the way, now that these are different memories, instead of having two instructions, we basically just have one instruction. So if your function's small enough, it's one instruction per function application, right? So in this template memory, you've essentially got some representation of a let expression in some ANF. So you've got bounds on the number of let bound applications, you've got bounds on the length of each of those applications, and a bound on the length of the scope. But really, it is just a single let expression. The other thing they introduce is, you'll notice there's a new case alternative stack. They made the choice of actually having first-class support for data constructors and case expressions. Previously, that was all just encoded as lambda calculus stuff. So that gets you a slight win. You have to do one fewer layers of function application to get your answer there, usually. The other win, though, is moving some of that accounting out to its own stack means you always know exactly where to look when you're trying to jump to the right alternative. If you don't have that stack, you're looking at different points on your main stack, depending on the arity of your constructor, and it gets a little bit messy. One of the really neat things they also added is to do with the handling of primitives. So they noticed if we're doing a function application and it includes some primitive operation, it wouldn't cost us any more just to evaluate that primitive operation than it does to construct it and dump it on the heap. So again, dynamically at runtime, they'll look at the arguments if they're already evaluated, instead of just kind of allocating it, dumping it on the heap. They'll just reduce it inline. So in your function application, you're also potentially getting some extra computation that happens. So for our own work, we've taken all of those ideas, extended them a little bit further so far. Architecturally, big difference is we change how we deal with primitive operations once again. So the observation here was, in hardware, it's very cheap to make these parallel stacks. But it's not always very easy for us to map the user's program to actually make use of particularly wide stacks. Often it's all quite narrow spinal applications we're working with. So a little trick to try and improve the utilization is moving primitive operations into postfix. So what that lets us do is rewrite something like this. We're keeping the fx and gy in prefix. It's only the primitives that are postfix now. So we've got this nested application. We can turn it into a single wide flat application. So we don't waste time allocating fx and gx and then later dereferencing them. We just dump it all in the spine, in the stack even. There are some kind of hazards that can happen in reducer-on between consecutive cycles. Often we'll have to do some prefetching from the heap or code memories. And that means we can kind of oversubscribe the number of ports we actually have available. The previous approach to dealing with that is very, very conservatively using the templates. So that was all handled in the compiler. We've moved all of those dynamically into the runtime again at not great cost, but we do get some modest improvements from that. And we also fiddle with the way we represent case expressions. So we'd find really trivial base cases in recursive functions would end up taking a lot of space in the code memory, right? Because these are all fixed size, big templates. If we make some minor adjustments, we can encode the really trivial ones just inline in the stack instead, and we end up saving a lot of space in our code memory. So can talk about some numbers. So there's a lot more analysis in both the previous presentation and in the paper that's coming out soon. But the sort of summary for our implementation of the circuit anyway is we've implemented it in Clash, and we've made it kind of parameterized by the different dimensions you'd expect of that let expression we're instantiating. So the sort of best configuration we have for our test suite anyway is a heap with applications that are 6 elements wide and stack where we can permute any of the top 8 elements. That gives us a circuit that seems pretty slow, right? Sub 200 meg. We'll see that we're doing enough work per cycle for that isn't a killer yet. This is actually exactly double what Reduceron had in 2012. And a lot of that, most of that is just us riding the wave of the underlying FPGA technology, right? We've done a little extra fiddling with the vendor tools, but most of that is a completely passive win. Another interesting win is going from 90% usage of the contemporary FPGA for Reduceron with the same memory sizes on a pretty decent FPGA now, we're under 2%. So there's like real low-hanging fruit for exploring multi-core versions of this, right? And the additional kind of active changes we've made to the design, we get modest benefit to both the number of cycles it takes to evaluate any of these benchmarks, the code size, and also the number of allocations. The number of allocations will be particularly important when we're looking at garbage collection, but everything I'm about to show you for a couple of slides ignores it because I've not talked about it yet and we've not rerun a lot of the scripts. So let's look at some of the actual performance numbers then. We've run our entire test suite on each of these data points. We normalize the runtime versus the results from Reduceron, and we put them on the y-axis. On the x-axis, we've got an estimate of the power use. You'll notice there are 2 points for our own design. That is because this guy, that's the one we can fit 50 cores on, kind of. Well, we're using under 2% is a better way of saying that. So much of that power usage is static. It's basically just keeping the lights on in this big design that we're using very little of. So we've also built it for a much smaller, slightly slower device where we can fit about 3 cores. So the power usage there is a little bit more commensurate. So let's compare it with some CPUs running GHC compiled code. If we look at some examples of embedded ARM cores, we can see that we're looking actually pretty healthy with this small implementation, the Alternating 2.6 one. So we're either about 2.5 times faster on average or 5 times faster with a very slightly smaller power budget. That's pretty cool. Usually when I give the talk, I have to say, well, yeah, but do people use this in the embedded space? but luckily Carl set me up this morning. So, so there could be some interesting things in there. I don't know how much of that we will explore in the embedded space. The more challenging comparisons for us are when we look at any of the even mobile or desktop or server CPUs. So if you only care about absolute performance, and sometimes you will, sure, a really decent desktop or even modern mobile processor, you're looking at 2.5 times faster than us, which is fine. That gap has closed a bit though since the last Reducer-on paper. That was 4 or 5 times they were reporting. But really, if you're looking at either extreme, so in the embedded space or in something at scale, you probably care a lot more about performance per watt than you do absolute wall clock time. And in that case, we have our outlier here. If you crunch the numbers, I think that was 1.7 times this guy, which is the processor in this laptop. And that's what we think is encouraging, right? If we can make that scale to multi-core architecture. Yes, Sam?
Thought about what this might look like normalized for technology nodes, because I presume the A9 is on like 40 nanometers, and some of the more recent i7s are on like 10 nanometers or something, and the FPGA
that is a very good point. I haven't, but
you can play around with numbers and get a very approximate answer, right?
Okay. Yeah, I'll give that a look. Thank you.
You could look at 28 nanometer A and B, you can still find them.
Yeah.
They're TSMC because those are definitely TSMC 28.
Otherwise, if you look at press conferences from TSMC, people will tell you what their performance changes like from generation to generation and power and stuff. Okay.
Great. No, I'll give that a look. But this is already the sort of encouraging point for us. If we make that scale, then we might get some good results at the end of the project. But actual review, totally fair enough. All we're doing here is we're filling up the heap and then making it fall over and then pressing the restart button. So we really do need a garbage collector. And I will blast through a little bit about our early work towards the garbage collector. So we're doing a really textbook mark and sweep. There are some extra features around it though, to make it work actually concurrently to the reduction. So on the left, we've got our reduction core. That's everything we've seen up until now. And then we've got some new memory management unit on the right. And sure, they'll both need to access the heap. So let's arbitrate that access. Always give priority to the reduction core. If we stall the memory management, that's no big deal until we're totally out of heap space. Ideally, we'd want the communication between the two cores to be quite simple. So the memory management core just has to present valid free addresses to the reduction core. It has to present a couple because the reduction core can allocate several things in one cycle. And in return, the memory management core is told which addresses have actually been used. That's the ideal case. So we're taking some inspiration from Martha Barker's paper from FPL a few years ago. And the way we handle this allocation is having some control logic and only one kind of bookkeeping block RAM. Each node in that block RAM just has a tag and a heap address. So all we're doing there is maintaining a couple of different linked lists. The most important one being our free list. So linked list of all the things that are still okay to allocate. There are a couple of difficulties though in this allocation. We need to always be able to present at least 2 valid free addresses. So the dumb thing that I've decided to do is just maintain 2 unique free lists, each with their own accounting. Even worse though, we've got these registers just to help our timing on the communication paths between the two. And that means the reduction core doesn't know what, well, the memory management core doesn't know what the reduction core is doing at any point in time. It just knows what it did in the previous cycle. So all of our tricks to make popping something from the free list happen in a single cycle gets a little bit tricky because we don't know when to actually perform that. We only know one cycle later. So to kind of hide that latency, let's just maintain 4 different free lists, right? Each channel has 2 of them. As soon as one's been used, swap them around and present the other valid free address and give us some time just to update. So that brings in a few issues with actually keeping those free lists balanced. If any of them becomes exhausted, then we have to stop what we're doing. And again, that latency is kind of difficult for us to handle. We can kind of get around things though by having a really simple kind of predictive signal here. So the reduction core says, I know in the next cycle, I'm definitely not going to allocate anything. And when that happens, we're free to do all of our redistribution. So we also have to deal with graph updates. That's also something new versus Martha Barker's work. But the real winner here is that update avoidance scheme we had. Whenever we dereference some pointer that is definitely not shared, we can just send that along, say, this is a thing I know I'm never going to need again, just free it now. So if your program is particularly linear, that massively reduces the amount of garbage collection you have to do. Averaged over a whole benchmark suite, that catches 50%, a bit over 50% of all garbage. And it's a feature we already needed for a completely different optimization. So that's the really neat win here. Yeah, pretty textbook Martin suite. We try and keep the reduction core running as often as possible. And final thing then, a little sneak preview of some of the results here. We've plotted the percent of garbage collection overhead in 3 benchmarks for GHC, reducerons, copying, like 2-space collector, and our own. And our own is actually hiding down here. So as long as our heap size is big enough versus the peak working set, there are situations where we never pause the reduction. We do spike up a little bit at the end, but nothing compared to the other 2. This Braun example is extremely linear, and all of these data points down here, because of our dynamic analysis there, they're not close to 0. They all are just 0. So we are basically, our next step is to look at multi-core architectures and how we can squeeze out some implicit parallelism there. So we've got a core that tries to evaluate these things as directly as possible. It's pretty small. We can, possibly fit up to 50 of them. It's not that slow. So versus Rob's laptop, 5 out of the 6 benchmarks we have do run faster on our design. There are neat things in that there are some techniques that wouldn't make any sense to do in a software implementation, like all these dynamic analyses, that become really, really simple with custom architecture. And finding those has been kind of the most exciting part of this project so far. And yeah, we're basically going to move on to looking at multi-core and parallelism stuff very soon. But that's it for me.
One question.
Sorry, my bad.
It's all yours.
So as Carl showed, memory access is the expensive thing. Your laptop is using DRAM.
Yes.
So do you know whether DRAM was accessed at all when you were running your program, or everything was run from L1 cache?
Well, the examples
Because
are,
the transfer that's probably 3 watts easily from your 4-watt budget. So
yeah, okay,
on the i7. So
yes. So I don't know quantitatively if that is the case, but all the benchmarks are small enough that I imagine there wouldn't be too much DRAM.
you could look
uses.
at the
Yeah,
performance counter, see
Yeah,
how
for
many
sure.
misses you have.
Yeah, that's very true. I should look at that.
Okay.
Yeah. Okay.